Swayam Prabha. Digital India. Educated India.
I am trying to make this course as independent as possible to that course, but there will be some points where you may have to do a little more work to get in pace with what we are trying to teach here, because your digital course essentially dealt with only logic minimization, but logic minimization and some counter design, etc., hardware design, but that was actually 1/5 of the course of our course. Okay, so they have learnt 4/5 more than what you have learnt in that course. So we will try and bridge the gap, but I should tell you that you have to do a little more homework to see that these gaps are bridged. Okay, so that is one thing. So with this as the background, let me start this course. Again, this course, there are 3 pillars to computer science. The one is the computer architecture and organization. Another course is the operating systems, which we will be doing in the 5th semester, and then compilers. Again, you will be doing in the 5th or 6th semester depending upon the curriculum. Okay, and these 3 pillars actually hold key for you to be a good computer science and engineering student. Computer science is all machine learning, all this stuff. Computer engineering is another suffix added to your degree called engineering. And to be a good computer engineer, you need to understand these 3 subjects in great detail. So this is the 4th semester course. We will be doing this now, and then of course the other course. And please note that all these 3 are highly interrelated. So a lot of concepts in organization will be used in OS and also in compilers. Okay, so be very attentive in the class and try to understand. And the way I have structured the course is that every time I talk about some concept, I will also talk about the operating system issue of that and also the compiler issue of that. Okay, and there are a lot of books available in the market. So a lot of books will teach you how and what, how something is done and what is done, but they will fail to teach you why it is done. Okay, there are several reasons for why the books are missing this why part. Okay, but we will not go into that. But this course I will be basically teaching you why certain things are done. What is the rationale behind those things, and you have to understand that so that we make best out of it. Okay, and understanding that why is very crucial. Fine. Okay. So when we look at the organization of a system, there are 5 levels in the organization of the system. One is the basic digital hardware. On top of it is the what you call as a micro architecture. On top of it is the operating system, then the compilers, then your application software. So there are at least 5 levels that you need to study to understand the system. Correct? Now please note that each level is isolated from the remaining part. So each level I could call it as a virtual machine. So I can say virtual machine 1, virtual machine 2, virtual machine 3, virtual machine 4, virtual machine. And each of this has a language. For example, the application software is basically written in a high level language like C, C++, Java. Then there is an assembler which actually converts this high level language into a language that is understandable by the hardware. Right. So when I look at say hello world.c. This is a high level language program. This gets converted to some a.out. The software involved in this conversion are the compiler and the assembler. So, from the application software here, there is a compiler which actually converts it into an assembly language, and there is an assembler which will convert it into zeros and ones. So, this is the machine language, right. So, there are two translations that happen. The first translation is the application software getting compiled into an assembly language program, and then the assembly language program getting converted into a machine language. So, this virtual machine that you see on the topmost layer can understand one language, which is the high level language. The compiler basically takes the high level language and converts it into an assembly language. The microarchitecture can understand only the assembly language, or it can understand only the machine language. So, there is an interpreter or an assembler which will convert that compiled assembly language program into a zeros and one, which is the machine language. So, every machine here, the virtual machine here, essentially has an input language and an output language, or what you call as an input, a source language and a target language, right. And so, there is some conversion process. So, when we go from top to bottom, the topmost layer is the one that is understandable to the human being, easily understandable, and as we go down the stack, it becomes more understandable to the hardware or the machine, right. So, there is a gradual decrement in the abstraction. At the highest level, I have a very high level of abstraction, and as I go down, the level of abstraction comes down, and finally you land up with ones and zeros, which your microarchitecture will execute. Intermediately, there is one layer called operating systems. One can use different. Wow. Okay, one layer called operating system. So, there are certain functionalities which your program cannot directly execute, it needs a help of an operating system. For example, in the hello world you have printf. You never write the code for printf, so you ask the help of someone, and that someone is the operating system. So, the operating system basically tries to satisfy some of the needs of your application software, right. For example, in the assignments that you did, you used lot of classes and libraries, correct, your math library, your memory allocation library, so many things that you used in your assignment here, correct. Those we claimed as, those are some of the facilities provided to you by the operating system, right. So, there are functionalities that are basically done by the operating system, and those are the things which are required by the application software, right. So, in this entire organization, we call this as a structured computer organization. So, in this structured computer organization, every machine, I call it as a virtual machine in the sense that the person working at that level, for example, if I am writing an application software, I need not really bother who is going to compile my code, what is the underlying architecture. So, the entire thing below the application software, the 4 layers below the application software is completely hidden to me. For me, I see a machine which will take a C program and execute. How it executes is not my problem, right. So, that is why we have this adjective virtual there, right. It is a virtual machine because we are not bothered about the layers below that. And so, if we take any layer, say for example operating systems, so it has an isolation from the other layers. So, every layer is completely isolated from the other layer, and that is the reason why we call each of these layers as a virtual machine. Okay. So, now this course essentially talks, we can call it as computer architecture and organization. some years before these two were taught as separate courses, but there is no point in teaching them as separate courses, because if you do not understand the underlying architecture, then you cannot understand the organization and vice versa. So we know, and unfortunately our BTech curriculum is so packed that I cannot have two core courses, one for organization and another for architecture, correct. So what we are trying to do is that we will try to teach you both in this course, right, and the way we have structured. So first and foremost, one fundamental question is, what is the difference between computer architecture as a subject and computer organization as a subject, right. Now why did I create this? Why did I create microarchitecture? Why did I create a digital hardware? Because somebody wanted it, correct. If nobody needs it, then there is no point in creating it, correct. And so who is needing this? Who is driving this? From say a calculator, today we are having a mobile phone with 8 processors. Who drove it? Right? The customers. Now how did the customer go? So the customer's need is reflected to the hardware through what? Through the software, through the compiler, through the operating system, right. The compilers grew in strength, the compilers became more complex, they started supporting variety of features, right, they started supporting variety of computational processes just because the user wanted it, correct. The operating system started supporting, say it is now supporting large amount of memory, it is supporting large different functionalities, different types of libraries. What is the need for the operating system to do it? Because the user wanted it. There is some programming environment, there is a software requirement, there is an information technology requirement which is forcing the user to basically to ask certain functionalities from the underlying programming language and the operating system. And if he starts asking those things, then ultimately your compiler grows and your operating system also grows in terms of the required functionality. And those functionalities it has to realize they are all software, right. Operating system is a software, compiler is a software. And how will they realize that functionality? By executing on the hardware. So that means they will require some support from the hardware, right. You understand this, right. So what are the supports that are needed, and how will the operating system and compiler communicate with the hardware to get that support? So two questions we need to answer. What are the supports that are needed? What support is needed? How will the compiler / OS get that support? From the microarchitecture. These two questions need to be answered. Answer to these two questions form the subject matter of what we call as computer organization, right. We want to answer specifically what sort of support the modern operating system is asking the hardware, right. I can give you a lot of examples here, right. For example, if I am looking at a real time system, I did define what a real time system is there in the previous, right. Do you remember? Forgot. Okay. So what is a real time system? Can you give an example of a real time system versus a normal system? When you drive a car, there is some electronics that is supporting your braking system. Is it a real time system? Yes, right. A normal system is one where the correctness of execution is determined by if you get a correct result. A real time system is one where the correctness of your execution is determined by not only the correct result but also the time at which that result comes, right. If you brake, if you apply brake, the car should stop, that is a correct result, but then it should stop within the next few seconds, then only it is correct. So you apply the brake and then it does not stop within the next few seconds, it dashes, then it is not a correct result, right. You understand? So a real time system is one in which the correctness of execution is not just the correctness of the result alone, but the time at which that result is manifested, okay, right. So when I start to, so suppose I want to design a real time system, there is an operating system running there, right. The operating system responsibility of that software is to see that I give you a service the moment you ask, very quickly within the deadline, you understand this. Now when I want to design a real time system, how will an so suppose I am putting a computer in a car to basically look at braking, right. How will the processor in that computer understand that there is a brake that is necessary, there is a that it has to act on a braking routine? How will it realize that there is a brake that is applied? Can you give me a mechanism by which it can? No, that is how the brake comes up, then how will the processor realize it? Electric signal will come, and then it will come in the form of, so you type, you just press the keyboard, how will the system realize that there is an input coming from the keyboard? Then there is some, basically there is an interrupt, right, there is an interrupt that is coming up. Now in the case of the real time system, that interrupt should reach from the time the interrupt comes to the processor, the time that the processor realizes that the interrupt has come, right, that time, what you call as the first response time, should be very, very fast. So when I am designing an architecture and hardware for implementing real time system, one of the things that I need to ensure is there should be a fast interrupt path. You are understanding this? So because once the interrupt comes, I cannot take long time to realize that there is an interrupt. So when the interrupt is generated using your piezoelectric or whatever, when the brake is applied, the interrupt is generated, from the time it is generated till the time the processor starts responding to that, right, it should be very, very, very fast, right. So that is a requirement from the user or the operating system. If the operating system says I am responsible for the safe running of this car, then it says the hardware, hey, please give me a very fast interrupt response. Then I should design my architecture in such a way that the interrupt response is fast, correct. Are you able to follow what I am trying to say, right. So what sort of support is needed and how will the compiler OS get that support from the microarchitecture? These are all subject matters of computer organization, and I have just told you one such need or support that is needed by the operating system in one context of an automotive example. Now this is also called, like you have API, right. What is the expansion of API? Application Programmer Interface. This interface is called ABI, Application Binary Interface, right. Now understanding this ABI is the subject matter of computer organization. Now that I understood what are all the support needed, right, the type of support needed, how will I build that support in the underlying hardware? How the support is built at? How the support is built? So this answer to this question is the subject matter of computer architecture, okay. In my opinion, computer organization cannot be taught as a theory subject, okay. So computer organization, if you say I am going to teach, it is a stupid thing in my opinion, okay, it is strictly my opinion. There are n universities and n profs teaching this. So I am going to align computer organization with the lab. So the computer organization will be taught during the lab hours along with the experiments. So I will teach something immediately that evening. If you spend that 2 hours, you will finish off, then do not bother till next Tuesday, okay. So every day we will give you some exercises and ask you to immediately go and implement it and see it for yourself, and we are giving you an excellent environment using the most complicated processor ever done in the globe, called the AMD or the Intel platform. We will teach you a lot of things there of what could be a possible good application binary interface. and we will make you work on that. We have spent a lot of time in creating that environment, which is now available. I hope all of you bring your laptop, and I actually shared the links to all of you. I hope at least finish the installation. I will talk about it tomorrow also. Okay. In the theory class, I will cover architecture and then relate it to what is happening in the organization. Okay. So, we have to answer both these questions in this course, so that we get a good understanding of what is computer architecture and organization. Okay. Fair enough. Okay. Chal. Now, so we will now start with hardware, basic digital hardware, right. Now, we will start with the basic unit of operation called addition. Okay. Addition and multiplication. I will teach you one very good adder and a very good multiplier. Once I understand addition, automatically you would have understood subtraction, but anyway I will cover some basics tomorrow. Then we will look at some division algorithms, okay, and then we will also look at the IEEE 754 floating point representation. It is also extremely important. Okay. So, we will look at these floating point operation, how floating point division is basically carried out, how floating point multiplication is carried out, right. So, we will look at this thing for 2 weeks. We will concentrate on high performance circuit design, right. Okay. Right. So, these are some things which are not covered, it was not covered for the Palakkad students also. So, I have not covered that in the foundation system, because it is supposed to be covered now. Okay. So, we will do this in the next 2 weeks, okay, and I will try to make it as interesting as possible, but it will be interesting. So, we have some very interesting ways of implementation. Okay. Now, let us start with this very interesting technique called recursive doubling technique. Okay. I want to find the prefix sum of 8 numbers. What I mean by prefix sum is, so I want 0, 0 plus 1, 0 plus 1 minus 2, 0 plus 1 minus 2 plus 3. So, this is 0 plus 1 minus 2 plus 3 plus 7, okay. 0 plus 1 plus minus 2 plus 3 plus 7 plus minus 8 and so on. Okay, this is called prefix sum. So, at the end this will have 0, this will have 1, this will have minus 1, this will have 2, this will have 9, this will have 1, this will have 7, and this will have whatever 7 minus 15, okay, minus 8, okay, or vice versa. Okay, I think we could also, yeah, vice versa. Say I want minus 15, I want minus 9, I want no, this way. Okay, so if you do this, so if I keep summing this, I have A0, A0 plus A1, A0 plus A1 plus A2, A0 plus A1 plus A2 plus A3, A0 plus A1 plus A2 plus A3, and so on. Suppose I want to do this, okay, and I do it on a normal system, right. How much time will it take? Assuming addition takes 1 unit of time, how much time will this take to add these, to get these results? Huh? Assume this is an array. How much time will it take? 7 units of time, right. Now, can I do it faster? Let us assume that I have a processor for each one. So, I have 7 processors available to me. Can I do it much faster? This is a question. You are understanding? So, if I have 1 processor, it is going to take 7 units of time. I have 7 processors, can I do it faster? Okay? So, what I do is, this is the algorithm, very simple algorithm. What I do is, at every step, so at every step, I add the number to which I point and make this is the first step, and second I will point to the pointer of pointer. For example, I will add this element will add 6 to minus 15, so that means you get minus 9, and it will now point to 5, pointer of pointer. So 15 minus 7 is pointing to 6, 6 is pointing to 5. At the end of the first step it will now point to what? It will point to 5. And similarly, what will 6 do? 6 will add to minus 8, so you will get minus 2, and it will now point to 4. You are understanding this? So I will add to whomever I am pointing, the content of whomever I am pointing, and then I will point to that fellow's pointer. So are you able to follow this? This is a step. So at the first step I will add minus 15, 7 points to 6, so the content of 7 will be added to content of 6 and stored at 7, and now 7's pointer will point now to 6's pointer. Similarly, 6 is pointing to 5, so the content of 6 will be added to content of 5 in parallel, because I have one processor for each, right. So in parallel I will add 6 to minus 8, and now 6th pointer will be pointing to the 5th pointer, so 6 to 4, and so on. You able to follow? Yes or no? Okay, now you see. So this is the step 1. After the step 1, please understand that 7 has minus 9, 6 has minus 2, this has minus 1, 4 has 10, 3 has 1, and 2 has minus 1, and they are pointing. So what will be here? This will be A7 plus A6, A6 plus A5, A5 plus A4, A4 plus A3, A3 plus A2, A2 plus A1, A1 plus A0. Okay. So at the end of my first step, I have added a number which is 1 away from me. Every element has added a number 1 away from it, and it is now pointing to a distance of 1 away from it, right. So now please note that whatever is the content of this location is A7 plus A6, and it is currently pointing to a location which is storing A5 plus A4. Similarly, whatever is stored here is A6 plus A5, and it is currently pointing to a location which is storing A4 plus A8. So in the next step what will happen? Minus 9 will get added to minus 1, right. That means what will be stored here? It will be 7 to 4, because here currently it has A7 plus A6 and I am pointing to A5 plus A4. So I will have 7 to 4. What this is having 6 to 5, and this is 4 to 3, so this will have 6 to 3, and this has 5 to 4 and 2 to 3, so this will have 5 to 2, sorry 3 to 2, and this will have 4 to 1, A4 plus A3, this stores A4 plus A3, and this is pointing to A2, and this will have 3 to 0, and this will have 2 to 0, and this will have always 1 to 0, and this will have 0. Able to follow? Right? At the end of the next step, when I click this, that is step 2, these elements will now store from, because currently it is storing 7 to 6 and it is pointing to 5 to 4, now this will become 7 to 4, correct. Now where will this point to? This will point to pointer of this, so this will now point to this. At the end of, when I go to at the end of step 2, what will happen? This now will store the values from A4 to A7, sum of A4 to A7, and it will now point to what? Sorry. This will now point to things storing 3 to 0, correct. You are able to follow this? Okay. So let us see what is happening at this end. This will store 7 to 4, 6 to 3, 5 to 2, 4 to 1, 3 to 0, 2 to 0, 1 to 0 and 0. Okay. This is at the end of step, and in the end of step 3 what will happen? This 7 to 4 plus 3 to 0 will become 7 to 0, 6 to 3 plus 2 to 0 will become 6 to 0, 5 to 2 plus 1 to 0, because 5 to 2 is pointing to 1 to 0, this will become 5 to 0, 4 to 1 plus 0 will become 4 to 0, 3 to 0, 2 to 0, 1 to 0. So next step what happens? So you will have the answer from all, and this is the answer, this is the step. You are able to follow this? So if I have n processors, so at every step I add the number to which I point, I add the content of the location to which I point, and I make my pointer as pointer of pointer. If I keep doing it, please note that at the end of a step, first step, I am pointing to an element which is 2 power 0 away from me, and I have added 2 elements. In the end of next step I am pointing to an, so at the first step I am pointing 2 power 0, at the second step I am pointing so this is 2 power 0, at the end of first step I am pointing 2 elements away from me. So this is the 2 elements, if you subtract the index it is 2. At the end of the second step I am pointing to 4 elements away from me, right. So at the end of k steps I will be pointing 2 power k, so I stop when 2 power k is equal to n, so that means k is log n. So if I have n and note that all the operations I do in parallel, correct. So every step is done in 1 unit of time. So there are 7 processors, and each processor in concurrently in parallel just goes and adds to what I am pointing to, and then makes my pointer to pointer of pointer. You are able to follow? So in log n steps I will be in a position to finish off this prefix sum. So if I have one processor I am going to take n steps, but if I have n processors I can do it in log n steps. Why is this possible? Because we are doing addition. What is addition? Addition is a associative operation. Okay. Since I am doing addition I can do it because I assume that the operation that I am doing is an addition, is an associative operation. If it is not associative, then a plus b plus c is not equal to a plus b plus c, meaning if plus is a non-associative operator. If plus is addition, then so I can do this for any associative operator. Please note that this algorithm will not work if I do not have if the operation that I am defining is not associative. Correct? You got this? So I can do this operation, I can do prefix min, I can do prefix maximum, because maximum of a comma b, max of a comma b comma c is max of a comma max of a b comma c, right? Max of a comma max of b comma c is equal to max of a comma b comma c, correct. So max is an associative operator. Similarly min, so I can do similarly multiply, okay. So I can do prefix addition, prefix sum, prefix maxima, prefix minima, prefix multiplication, okay. So we will just stop here. So this particular concept of what we call as recursive doubling will be used to construct an adder, okay, and we will see how we are going to do that in tomorrow class. Okay.